Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I'm super happy to have Rebeca Batalha with us today. Hey, Rebecca.
Hey, Frank.
Boy,
it's nice to me to be here.
Well, thank you very much for agreeing to talk about your super lovely article. It's very nice. And Rebecca, where are you located at?
So I'm right now in Rio de Janeiro.
Rio.
It's in Brazil. So I'm doing like I'm finishing my PhD here actually in 2 weeks.
All right.
Yes.
Well, congratulations.
So, thank you.
We get to call you Dr. Batalha.
Yes. Hopefully.
That is awesome. Good. Well, congratulations on that. That's really awesome.
Thank you.
And let's see, so you're going to be graduating here in a few weeks, and so Southern Hemisphere spring must be coming around.
Oh yeah, I mean it's kind of cold here, weird for this time of like this period of the year, but it's fine. I mean it's better than so much hot. Like
oh yeah, oh yeah, very cool, very cool. And Rebecca, what do you like to do for research? So
I basically really like to research about galaxy clusters. I find they like amazing because they involve all the specific astrophysics, you know, so you have to understand a little bit of stellar astrophysics and also galactic and the whole thing. So I think that's amazing.
Very cool. And this is going to bring us to this very awesome article. This is an APJ supplement. It's open access. People go grab a copy for free. And ranking theoretical supernovae explosion models from observations of the intracluster gas. And Rebecca, take us away.
Thank you very much. So, so as the title says, I'm basically comparing the models, the simulations, theoretical simulations that there are in the literature, and compare the ones that have like makes available the final products, nucleosynthetic products. They can be compared with what we observe. So what I'm doing here in this article is comparing what models, theoretical model predicts with what we observe in intracluster gas. Okay, so I would say that's what the title says. So the motivation itself is to understand how the intracluster gas is enriched. Okay, so there are like different enrichment mechanisms involved, and also different ways to tackle this problem. So here, so let's start because 4 years ago, we found out, like the community found out that the intracluster gas is enriched, okay? So you find the metals there when you look at the X-rays. So that's basically a link between what happens in stellar and supernova remnants to a greater scale, right? Okay. So that's interesting because we can find out how the process involved to transport these metals from interstellar medium to the intracluster gas. Okay. So to do this, we need to understand better supernovae because, as you probably all know, there are a few uncertain things about supernovae. Like for supernova 1A, we don't actually know about the companion star, so you can simulate a model that has another white dwarf, or a model that has actually an evolved star. So this final model will produce a different nucleosynthetic product. So you can collect lots of models in the literature. That's what we did. Indeed. We collected 263 models.
Wow.
That's why it's long. And we basically were trying to ranking to classify how they are in agreement with the observable abundances. Okay. So to do that, we then look at the intercluster gas in X-ray using Observato satellites for 18 nearby galaxy clusters in groups.
Okay.
From it, in table 1, you can see that we collected a nearby sample, and in this sample you have actually many huge galaxy clusters and also some small groups. And if you look at column 5, you can see that we were looking at the core radius, because we are interested on understanding how the enrichment happened. And the enrichment could happen different importance in different places of our clusters. Okay.
Yep.
So we separated them, this inner region that we call throughout the paper, which encompasses the full core radius. And this full core radius, basically, in the literature, we see that they have a central iron peak too. So we're trying to figure out how these two are playing together. Okay.
I'm with you.
So we have this inner region, and we have also the outer region. And those two regions, we are collecting measurements from abundances and calculate their ratio abundance. So we calculate 8 ratio abundances, oxygen, neon, magnesium, argon, so on, over iron.
Yes.
That's because type 1a supernova produce much more iron and iron group elements compared to the core collapse. So this ratio is actually helping us to quantify, to separate them in a better way, you know.
Yes.
So okay, so to do this, we are interested in looking at these different regions, but we also look at this all region, the entire field of view of each cluster as a control sample, you know. So we could say if these separate these two regions, would it really help it to differentiate between the models or not, for example?
Okay.
If it is true.
Mm-hmm.
You know? So moving on, we could let's see, we could say, could you a little bit further? Yes.
A bit further? Okay.
Yeah. Mm-hmm. So from here, we started them to thinking how we could connect it, the measured abundance on intracluster gas on this medium, hot X-ray medium, with the predicted ones from the supernova. So if you go to the equation 1, we actually built a linear combination.
Okay. Okay, I'm with you. Yep.
Yeah, great. So we here, this equation says basically what we see in the intracluster medium is actually a linear combination of what this model should predict. If a model, right, is predicting well what we see in our sample, for example.
Yes.
So we do with some algebras, really simple, but at the equation 4, if I'm right, yes, the 4, yeah, you can see that 5. So you can see that you can actually have a direct comparison between the ratio. The RE is the ratio of a given element E, okay?
Yes.
Measured in this diffuse gas, so observed, would be a linear combination of the ratios that these models predict. So I1 is the ratio of the model of supernova 1A of a given element E.
Okay.
Okay, so we have the same for the other one. So we have the ratio predicted for the model J for the core collapse supernovae model. Okay. When I say core collapse, I'm actually include the type 2 supernovae. I'm include also the hypernovae and peristability supernovae because the supernova 1A has some really specific enrichment. So that's we could do just two huge classes of supernovae enriching the ICM. Okay, so
Yep.
But how could we compare them, right? It's being done in briefly in the literature. People compare like a ratio directed to the predictive ratio of the supernovae.
Yes.
But we try to do that a robust way, so we could do the entire measurement as a probability distribution function. So what we did was developed a method that accounts the entire measurement. So to compare what we see from the predicted models with what we see from the observations. Okay, so to do this, we compared the cumulative distribution functions of using the KS test, the Komolov-Smirnov test.
Yes.
And we set a threshold to say that that they are not drawn from the same distribution, right? So the threshold is 0.05. And in the next section, I explain how I construct each of these cumulative distributions. So the first one is called empirical cumulative distribution.
Okay.
Which I call throughout the paper ECDF.
Yes.
So this ECDF is constructed. If you could go to figure 1, I could show you the probability distribution function.
Yep.
Yeah. So figure 1 shows the probability distribution function of a given abundance ratio.
Okay.
And this, yeah, that's great. So here you have the probability distribution function measured for each, in blue, measured for each cluster of the sample, okay? So you have the central normal distribution as the nominal value of the measured abundance, and its uncertainty, it corresponds to the deviation, to standard deviation. Okay, so in this way, we could construct actually a PDF that corresponds to the probability measurements of this sample, right?
Yes.
So far, that's it. So in figure 2, we calculate the CDF related to this PDF. Okay. So that's also the red curve. So this red curve is an example of the empirical CDF for silica over iron ratio, okay? So we construct that for each measured abundance, okay? Yes. So also the second part is now to compare the CDFs, construct the CDF related to the models, supernova models. So for this, we calculated the TCDF, which is the theoretical cumulative distribution function.
Yes.
This TCDF is, yes, great. This TCDF is constructed by the ratios of what this model predicts. Simple like that. So you have like the supernova 1A model. I put like an example here, okay? So it would be better to follow how it was done for all the 7,000 pair of models. So here we have the Iwamoto 1999, which is called WTD1, this model. Okay. And it predicts 1.067 of silicon over iron, okay? So that's why we have these thresholds here. So in equation 11, yes, this the same model. So if you see here, the probability is actually 0 before 1.067, fixed, you know, it should be 0 if this model is correct.
Right.
And
then
we weight a same probability between these supernova theoretical limits. So the other limits is delimited by the supernova collapse model that I'm testing. So here in this case is 4 point something. So that's why this value is going to 1 when it reaches this value, you know.
yes.
So all these pairs, the TCF were constructed like that. So we have this.
Yes.
So you have 2 CDFs, right? And from now on, you can just apply this KS test.
Yes.
And so the next figure show some interesting insights about this.
Okay.
I would say, because it shows that for it's for figure 4. So yeah, so figure 4 actually shows that different spatial abundances and different pairs actually produce different p-values. So you can see here.
Zoom in on one of those.
Yes.
Oxygen.
Of course. Yes, great. So here we have an example of oxygen over iron. So I'm applying this test. I'm comparing the 2 CTFs, okay, with the oxygen over iron PDF that I constructed figure 1. And after that, put a figure 2. So here you can see that for different pair combinations that you have, like in the x-axis, you have the supernova 1A model. In the y-axis, you have the core collapse supernova model, okay?
Yes.
So those different models are combined, and you can see that the different combinations actually yields different p-values.
I'm with you.
So that's how we can set the threshold, and we exclude the ones that is too dissimilar, you know. That's what we've done to get to the result. So we could actually classify and ranking the models, the pairs of models after this comparison between the CDFs.
Right. And p values, we want low p values, right?
Yeah. Yes, because if I set the threshold, so the lower p value is the pair rejected.
Yes.
Right. So I would say that their pair is not drawn from the same distribution of the CDF that I measured with we measured with the observatory abundance ratios.
Yes.
Okay.
I'm with you.
So
thank you. Okay, so these are 1As. So the silicon we covered before. So let's do silicon.
Yes. So you can see here, for example, that silicon can show too that these models are really different, like they predict different yields, and also they are evaluated different. Okay, so that's what we can see. That's only part of the supernova models, because as I said, there are a lot. So I just put it to show that that's the main takeaway from this figure, that you see that these different comparisons are showing differentiating between the models.
Yes, and yes.
So moving on, we could go to the results. So
I'm with you.
The next figure, I guess. Let me see. Yes. So from here we have the really ranking. Okay. So from now on, I'm showing this pattern of colors. Okay. Where the redder is the more rejected pairs, and the bluer are the least rejected. Okay. So the first result that we had when we ran all these tests was that no pair was rejected like by none ratios. Right. So every pair we had at least 4 rejections. So that's So that is in actually agreement with other papers too in the literature that they don't find a really good pair that's really good for describing the methods in the ICM, you know.
Okay.
But let's see what's going to take us later. So figure 5 is just showing the first result that we had, like some bigger picture first. So here you have the number of supernova pairs projected, okay? Remember that we tested 7,000, more than 7,000 pairs. So this solid red line is represented this number.
Right.
And the dashed line is half of it, just so we have an idea.
Okay.
So you can see that for each of these abundance ratios, we are rejecting more than 50% of the pairs. So
yes.
Yeah, so that's interesting. That says also that this method is effective to rejecting, to tell the differences between the ratios and between the pairs, right? Because one thing is with another. So that's nice of this figure. Figure 6, as I said, we look at different regions. Is under the,
Oh, there we go.
Okay, great, thank you. The top figure 6, we have also these bars, vertical bars, and remember I said that we had an inner and outer region. So we are trying to expand better the values and the ratios that could be different enrichments. That's why we did that. But we also have the measurements from the entire field of view. So if there is like if this was to test if there is some better efficiency to separate these regions, you know.
Right.
Otherwise, the results should be pretty similar, because the entire region is just a mean average of this inner outer region, right?
Right.
So what I'm gonna focus here is so the colored bar is using the inner outer relationship together to do this analysis, this comparison, and the hatched bars are using only the entire field of view measurements. Okay. So as I said, our main results show that none of the bars were rejected less than 4 times. So you don't see colored bars in 3 and 2. You only see in the 4, 5, 6, 7, 8.
8, right.
Okay. So
okay.
What you see here is that the power of differentiating these pairs are actually decreasing when you use the field of view, the entire field of view, because you have less number of pairs reject, like only 13%, like in the 8, for example,
right?
Compared to the 20%. So actually, it seems efficiency to separate these two regions to power this discriminative, to be more discriminative in this sense. So that's what we tried to show, but we also expected that the entire field of view region measurement would have also a similar behavior, let's say, because turns out that this is the mean value between these two regions. So we just expect like a smooth, like a smoother behavior compared. Yes, so we are very excited about this. It seems pretty nice.
Yeah.
And so all those two figures, the 5 and 6, we show just the general behavior, but we also are interested on some trends that can come from these results.
Yes.
So that's why we did the figure 7 as it is, because as I said, it's lots of pairs of models. So just trying to put them together will be challenging itself to us to read that, right?
Yeah.
So what we did here was trying to combine these two. So we have in the y-axis the supernova name models, okay, that we tested. So all the supernova name models combined with this, the supernova core collapse models. So you have, for example, Nomuro 13, the first one, supernova type 2 with 0 metallicity, okay? So we have these models and other from many authors and the literature.
Pretty impressive,
okay.
Actually.
Yeah, so in the horizontal bars, we have the supernova name models. We tested 2032, combining with each of these supernova core collapse models, okay? So what we look at this figure is how well or how bad these pair are evaluated when they are combined together.
Yes.
So the first bar, for example, you have that doesn't matter which supernova you're using, supernova pair you're using with these Nomuro 13 supernova 2Z0. They are all completely incompatible with the measurements part of them, no distribution, because they are 8 times rejected, which is the maximum, the 8 ratio that we measured.
Okay.
On the other hand, we can see that other pairs has actually a dark blue, large dark blue value. So we have 66, for example, in this case, pointed. Supernova name models that when combined with this supernova core collapse, Nomuro 06, supernova 2, 0.02 initial metallicity, are well behaved, I mean, are the least rejected in this case.
Yes.
So in this, we try to get together some trends, right, to understand better what if the comparison tell us something about the enrichment itself. Similarly, in figure 8, we did the opposite case.
Okay.
So we actually listed the supernova 1A on the y-axis and compare it to all supernova core collapse. Is a little bit difficult to see. You can take a look later with detail, but is actually similar interpretation of it. Okay, so yeah, I invite you to take a look, and if you like a model that might be here to see how is behavior compared to the other ones. Okay.
Boy, that is incredibly detailed. Okay, very good.
Yeah. So okay. So yeah, I think it's okay. So figure 10 is actually the main result. The next figure.
Good.
We actually had to put just part of it here. The other part, the detailed values are all in the appendix that you should take a look and more details. And here you can see that each supernova name model combined with each supernova core collapse model, how many times each was rejected. Okay, so remembering that you can be rejected at maximum 8 times because of the 8 abundance ratios tested.
Yes.
So here, for example, the red ones are the pairs that were rejected at 95% of significance level using our methodology, using these inner and outer regions from our sample of galaxy cluster groups.
Wow.
And yes, so as I said, we are trying to visualize better which ones are most rejected, but also which ones are the least rejected.
Correct.
Because that should be insightful for many reasons. One of them is trying to extend the intergalactic gas enrichment, intercluster gas enrichment, and also maybe some hints about which type of supernova A or each type of supernova core collapse are enriching these galaxy clusters and groups. So next figure is our final main figure in the paper, which gather all the supernova, all the least rejected pairs. Okay. So remember that we tested 7,000, more than 7,000 pairs, and now we have 229.
Okay.
All right. So we trying to help really narrow down all these pairs that we collected in the literature. Remember that all these pairs has their final nucleosynthetic product available, so we could compare like this. That's important.
Yes, very important.
Yeah, so here we found some interesting trends that we can see here. All in blue, all these blue squares are actually the ones that are evaluated at the least rejected. So in this case, in this study for this sample, are the best models, right?
Correct. Okay.
Yeah, so here you have that, for example, when you look at the y-axis, you see all these supernova core collapse models. They are basically all type 2 supernova models, okay, with no zero metallicity progenitor, initial metallicity progenitor. So all the stars that were simulated by these models have a metallicity different than 0.
Yes.
Okay.
Yes.
Okay. So that's what we find this trend as one of the main results. So it doesn't seem that it indicates, right, that this supernova models with progenitors that has 0 initial metallicity doesn't seem to be in agreement with our sample. On the other hand, on the supernova 1A side, we see actually that most of these models, the ones that have more flexibility on combining with the core collapse supernova, they are actually, most of them are 3D models. So it's cool because they have more detail and maybe they are more robust. More robust to explain and to simulate itself the exposure, right?
Yeah.
So that's nice. And they usually has also these typical central density that a wide dwarf has, that is 2.9, 10 to 9 grams per centimeter cubic. So that's one of the main results of our paper.
Very cool.
Which is actually being used to the next paper. So it was very, very useful to narrow down because there are lots of models in the literature.
Very
so let me see. I guess the idea of the paper is that I invite you to see more details, of course, on this. And
very cool.
Yeah, I think I'll leave you.
And just a reminder, we got 5 lovely appendices, so be sure to check that out when you get there.
Yes.
a lot more detail on some of the components. So it's
yes, on both the measurements and also the models. Oh yeah, because we have an entire table only explaining the basic feature of these models. So these models are different mechanism of explosion. So some then delayed detonation, others are double detonation, and new types of detonation that are coming in the literature. So you should check it out if you want more details of this model. So different ignition bubbles. So these bubbles can be in the center or not. So it seems like it covers lots of possibilities, you know, of both explosions and both range of masses too. So that seems pretty nice.
That's a pretty impressive collection gathering.
Yeah,
that's awesome.
Yeah,
wow.
We think to actually build a website so we could leave that online so people could, oh, how about this model? This model is good, or this model is in agreement with this sample of galaxy clusters.
Mhm.
So, because if you're looking at a higher Z redshift galaxy clusters sample, for example, it changed. I don't know, because these are really nearby. So we are trying to put this together on our website so it be usable for the community.
Yeah, awesome. I think, well, that's why it's supplement, because it'll have some applications elsewhere.
Yeah.
Very cool. Very nice. Rebecca, thank you so much for walking us through your very lovely article.
Okay, thank you.
And let me ask, where do we go? Where do you think we go from here over, let's say, the next 2 to 5 years? Are there yet more 1A models to gather, or type 2 models, core collapse? Are there additional observations that can be done, perhaps in wavelengths other than X-ray? That kind of stuff. So where do you think we go over the next couple of years on this topic?
That's a very great question. It can be answered in many ways.
Okay, I'm all yours.
First, on X-rays, I would say that X-ray is pretty efficient wavelength to look at.
Okay.
Because when you look at galaxy clusters, you look at this diffuse gas, which is splitting, and is usually well behaved. So when I fit a model there, it's usually I get abundances that are pretty well determined, you know. So that's one thing. I'll look at the, yeah, it's another way to try to differentiate between these models, because you could also look at the remnants, supernova remnants, of course, and look at directly of the supernovae. But you have multi-temperatures also, so it could be challenging. So that's one way. Also, of course, a better precision of abundances is always welcome. So the next generations of X-ray satellites will be grateful to that, not only on nearby system, but also in the higher Z system, redshift systems.
Yeah.
So yeah, both like Prisma and Athena will be really great for this.
Cool.
Yeah, I think that's all.
Perhaps you'll be maybe looking at some of these after you Dr. Batalha and onto your postdoc or something.
Oh yeah, I will like be on the postdoc closer to this area. Yeah.
Very nice. Well, cool. I really look forward to seeing this. Using this database and then seeing it further out, so we can even better determine, what are the progenitors of 1A and how do they, what's the population percentages of 1A versus 2s and so on.
Yes, exactly.
Very cool. Very cool. All righty. Well, thank you so much, Rebecca, again. And
thank you for the invitation.
You're welcome. And that will do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Bye-bye.